Hey guys, so I've always been fascinated by water. This is something so common in our daily lives, yet it's so complex. Usually, its movement cannot be predicted very easily, and it has many forms and shapes. But all of this complexity can be simulated by math. So today, I wanted to see how far I can push myself to build a fluid simulation from scratch using Python and Pygame. So before we get into the details, we must understand what a fluid simulation does. There are actually two types of fluid simulations. They're mostly either Eulerian or Lagrangian. So Eulerian is when you divide the space into squares or cells, and then you model the fluid in each cell. So you care more about the space and the environment than the actual particles. So this is usually used in large scale projects and weather forecasts. For the Lagrangian, you care about the individual particles. So each one has its own properties stored and they interact with their neighbors. And this is for smaller scale projects. So this is the approach I'm going to be using. You might be saying, you already built a particle simulator, then what's the point of building another one? That one is different because in a fluid simulation, particles can actually pass through each other. It's just based on the pressure. The higher the pressure is, the harder it is for the particles to just slide through each other. And also, they're controlled by pressure, viscosity, and gravity instead of just bouncing off. And essentially what every particle wants to do is move from denser regions to less dense regions. And this next part is going to be pretty mathematically heavy, so if you don't like, I suggest skipping ahead. So the method I'm going to be using is called smooth particle hydrodynamics. This bears some resemblance to the Navier Stokes equations, so some of you might recognize it. Like I said, the acceleration can be calculated from pressure, viscosity, and external acceleration such as gravity. The pressure is calculated by summing up all of the sample particles in the smoothing radius around a sample particle I multiplied shared pressure of those two particles by gradient of a smoothing kernel of your choice. You can use the poly-6 kernel or you can use the spiky kernel. In this case, I'm using spiky. And the viscosity is going to be equal to viscosity strength times summing up all of the particle j around this particle I, the difference between the two velocities of them, divided by the pressure of particle j times the ablation of smoothing kernel. So this kernel is actually different from the other one, the pressure kernel, because you have to use a specific viscosity kernel instead. And this is the equation for getting the pressure at a point from its density. We can multiply a stiffness constant or pressure multiplier by the difference between the target density, which is ideally what the fluid should have the density at all points, and the density around the specific point I that we're examining. This is also called the density error. If you're wondering what the smoothing kernel does, basically it calculates the influence of each particle j around the specific particle I in the smoothing radius. So you can multiply this influence value by whatever properties you want to calculate, like density or pressure. I've also decided to divide the screen into grids by size roughly equal to the smoothing radius, and so each particle only needs to look at the particles inside a 3x3 grid instead of every single particle on the screen. This greatly boosted my performance and simulation speed and allowed me to simulate from only around 200 particles to thousands of them. Now let's actually go over the code. So we have three files. The main.py will handle the graphics and control stuff, such as drawing text and reading input keys. The config.py will store all the variables and constants the other two files are gonna need. And the fluid.py is the heart of this project. So we start out by declaring a list of positions and velocities using either of these three spawning functions. You can start out with a grid of particles which is going to be a square, or spawn them randomly on the screen, or you can just start with a single one for fine-tuning parameters. In the update function that's going to be called every frame, we first initialize the grid by creating an empty 2D array, with each item being an empty list that's going to contain the particles' indexes in the velocities or positions list. Then we loop over every particle and look up which cell in the grid they belong to. Then register that particle onto the grid. There are also functions to print out the grid into the terminal or draw the grid onto the screen for debugging purposes. After that is done, we need to calculate and store the densities and pressures at the start of every frame, so we don't have to recalculate everything after. This will significantly save time and computational power and allow my simulation to be more efficient. And all of the operations shown here follow the equations that I explained earlier. Next, we can calculate the acceleration for each particle from pressure and viscosity using those values we got earlier and with the formulas I showed before. Add them all up along with gravity and the mouse interaction force, then we get the final acceleration for each particle. So before integrating and updating the velocities and positions, we need to compute candidate velocities with semi-implicit integration and clamp them. This will give the fluid a more natural feel and some sort of surface tension. Finally, we can check the particles' collision with walls and draw them onto the screen. So these are the kernels I'm using for my calculations if you're curious. Anyways, enough yapping, and here's the result. So I started out with the square cells spawn and debug mode on so you can see the grid. Each particle is also color-coded based on its velocity. You can change this anytime in the settings, just Google up matplotlib color maps. Right now, brighter color means faster and darker color means the particles are slower. You can also interact with the fluid using the mouse. Left click pulls them inward and right click pushes them away. You can also see the interaction radius where your force will be effective. My favorite thing about this simulation is that it follows the laws of real-life physics. You can see the waves moving around on the fluid surface. Later, when I start increasing the pressure, the particles will start moving more erratically and eventually turn into gas and fly around freely. They boil at the edges and on something called nucleation sites, which is realistic and physically accurate. Also, when I decrease the pressure, they clump together like a solid and behave like one. Anyways, this project was pretty fun and educational. Thank you guys for watching. I'll see you in the next video.